Good morning. In the material ahead, we're going to need to know a little bit about linear algebra. And while we have an entire course on that here at Austin P, I'm going to just say a few things as a reminder in case anyone's forgotten. The capital letter R with superscript n by m refers to a rectangular table of numbers. The R indicates that they are real numbers. N is the number of horizontal rows in the table, or matrix as we'll call it. M is the number of vertical columns. For example, this matrix A has 2 horizontal rows but 3 vertical columns. Matrix B has 3 horizontal rows but 4 vertical columns. This C has a single column. The D has a single row. When the context is clear, often people will say something like C or D, which has either only one column or one row. People will often just say R4 instead of specifying the 4 by 1 or the 1 by 4. We're going to define addition and subtraction of things like this. Also, we're going to define what it means to multiply something like this by a number. Suppose that you have 2 matrices A and B with the same dimensions, the same number of rows, and the same number of columns. When I write the name of a matrix with 2 subscripts, what I'm indicating is I'm looking in the row that corresponds to the first index, row I, and the column that corresponds to the second index, column J. We are going to define a matrix named A plus B. The numbers in A plus B are just the sum of the corresponding numbers from A and B separately. For example, 1, 2, 4, 6 plus 3, negative 1, 2, 5. 1 plus 3 is 4. 2 plus negative 1 is 1. 4 plus 2 is 6. 6 plus 5 is 11. Likewise, 1, 2, 9, 7 minus 3, 4, 5, 6. 1 minus 3 is negative 2. 2 minus 4 is negative 2. 9 minus 5 is 4. And 7 minus 6 is 1. If the matrices don't have the same dimensions, though, we don't define addition or subtraction of them. In linear algebra, when you write the name of a matrix with a capital T as a superscript, you don't mean A raised to the T power. People will laugh at you if you say that. You mean A transposed, or sometimes people just say A transpose. What you do is you make a new matrix. If the original matrix was in Rn by m, the transpose will be in Rm by n. What we'll do is we'll take every number that's in the A matrix and interchange its rows and column indexes to get something in the new one. So, for example, this has index 1, 1. If you interchange, you still have 1, 1. So I'll write that down here. In the original matrix, this has indexes 1 and 2. When I interchange those, I get 2, second row, and first column. This number is in row 1, column 3, so in the transpose, I'll write that number down in row 3, column 1. Second row, first column. First row, second column. Second row, second column. When you interchange the 2's, you still have a pair of 2's. Second row, second column. Second row, third column. interchanged third row, second column. Another way to say this is every row of the original will get written down as a column of the transpose. For this example, it's obvious that if I take the transpose of A transpose, I'm just going to interchange the rows and columns again, and I'll get back the original matrix. That turns out to be true in general. There's a concept of matrix times a vector. If A is an n by m matrix and X is a column with m slots in it, then A times X is going to be a column with n slots in it, and entry number I of this A times X will be, I'll take a number out of the ith row of matrix A, multiply it by a corresponding component of the column X, then do the same for the second component, and then just continue until I've added them all up. That is to say, it's done in this manner. I'll think about the answer, which is going to have two numbers in it, because I have two rows. To get the number that's in the first position, I'll look at the first row and the column of numbers that I have. 1 times 4, 2 times 1, 3 times 7, add them up. 4 times 4, pardon me, 4 times 4 plus 5 times 1 plus 6 times 7 for the second one. I'm not interested in simplifying the arithmetic, I'm just interested in the pattern. If the number of columns in the first matrix is not the same as the number of rows in the second one, we declare this to be undefined. Now, at the moment, we have only matrix times vector, to do matrix times matrix as well. We'll have a concept of numbers times matrix. All we're going to do is, if I have a number and I want to multiply it by a matrix, I'll simply take the number, 3 for instance here, and multiply the 1, 2, 5, and 6 by the 3. If I want to look at 4 times the column 1, 1, 2, it'll be 4 times 1, 4 times 1, 4 times 2. Again, I'm not interested in simplifying the arithmetic. If I have some vectors like 1, 2, and 4, 1, and -3, 1, column vectors that is, I could multiply any one of them by a number and get a column back, and I know how to add columns up. If I have a set of vectors and I take a number times one of them plus a number times another and so on, we call such things linear combinations of the columns that we're talking about. Or we'll have more general situations later. As before, the vectors have to be the same dimension. These column vectors have 2 slots in each one of them. If one of those columns had had 3 slots, then this wouldn't make any sense to us. If I think of the 2 by 3 matrix, 1, 2, 3, 4, 5, 6, multiplied by the column 7, 8, 9, it's direct to write out what the numbers are. I want to think of this a different way though. If you look at these two numbers, they have something in common. The first term in both sums have a 7. The middle term both have an 8, and the last terms both have a 9 as a factor. I can split this up into the sum of these 3 columns, and in the first one, since there's a 7 in both chunks, I can pull a 7 out, an 8, and a 9 in this one. This is very revealing. matrix times vector is the first number in the vector, the column vector, times the column 1, 4, which is the first column out of the matrix. The next term, 8 times 2, 5, is the next number in the column times the next column out of the matrix, 2, 5, and the last one is that number, 9, times the third column out of the matrix, 3, 6. When we do matrix times column, what we're really doing from one point of view is to just do some arithmetic. From another point of view, we are taking linear combinations of these columns, the coefficients of which are 7, 8, and 9 in this case, the numbers that are in the vector by which we're multiplying the matrix. If you take linear algebra or have had it, they make great use of this fact. This means anytime I'm interested in this kind of behavior, I think about linear combinations, whether I know it or don't know it. If I have a set of vectors, which for concreteness I'll take to be these 3 vectors, column vectors, if I multiply the first one by some number, multiply the second by some number, multiply the third by some number, and add them all up, I get a linear combination of those 3 vectors. Obviously, if I made C1 and C2 and C3 equal to 0, I would end up with the column vector of all zeros. Is there any other way of doing that? Is there any way to pick C1, C2, and C3 so that they're not all 0, and yet I get the column that has 3 zeros in it for an answer anyway? If it turns out that the only way to make this sum come up that is for all of the C numbers to be 0, then we say the set of vectors is linearly independent. If there's some way of doing it other than all of the C's being 0, we say that the set is linearly dependent. So let's calculate. If I multiply the columns by the appropriate C number and then add the resulting 3 columns together, I find out that C1 plus C3 needs to be 0, 2C1 plus C2 plus 3 times C3 needs to be 0, and C1 plus C2 plus 2C3 must be 0 as well. This is going to give me a little linear system of equations to solve. There are a wide variety of methods that I could think about to solve this. I could do Gaussian elimination, I could try to do Cramer's rule, I could do a variety of things, but I'm going to try to be sneaky. The first equation says that C1 plus C3 must be 0. If I write the third equation in a slightly modified way, I'll have C1 plus one of the 2 C3s plus C2 plus the other of the C3s, and I know that C1 plus C3 is 0. This means that C2 plus C3 must be 0. This tells me that C2 must be the negative of C3. On the other hand, the first equation says that C1 plus C3 is 0. C1 is the negative of C3 also. I'll think of giving C3 some particular value, which I'll call alpha. So C3 will be alpha. Because of what we just figured out, C2 must be the negative of alpha. And from the first equation, C1 must also be the negative of alpha. Alpha allegedly, if this calculation is correct, can be any number, and if you make coefficients that look like this, the linear combination of the three vectors based upon them will automatically come up 0, regardless of what the alpha is. For example, I can make the alpha -1 so that negative of alpha is 1, and allegedly there is a collection of coefficients, not all of which are 0. In fact, none of them are 0, but not all of them are 0, so that if I form this linear combination, I come up with a column of 3 zeros. Let's do a sanity check on that. A direct calculation shows that 1 times the first vector plus 1 times the second one plus -1 times the third one is, when the dust finally settles, the column of 3 zeros. These three vectors that we started off with form a linearly dependent set. They are not linearly independent. Another way to look at this is to write our results down again and then add the vector 1, 3, 2 to both sides. And then, of course, you see that 1, 3, 2 is 1, 2, 1 plus 0, 1, 1. If a set of vectors is linearly dependent, then there's at least one vector in there someplace that can be written as a linear combination of the other two. This is going to be important to us when we talk about a basis. The span of a set of vectors is the collection of all linear combinations of them. So, for example, the span of these three vectors we were just talking about is the collection of all things that look like that, where C1, C2, and C3 are real numbers. I have 3 vectors. You might think that this is going to be enough to map out all of 3-dimensional space, but it turns out it's not true. Because of what we just found out about these 3 vectors, if I form a linear combination, I could write down C1 times the first vector plus C2 times the second vector plus C3 times the third vector, but we made the discovery that that third vector is the sum of the first 2, so I could write it this way. It turns out that any linear combination of these 3 vectors is actually a linear combination of the first 2. If I have a set of vectors and I want to think about all of their linear combinations, if there are linearly dependent vectors on my list, I might as well erase them and realize that I don't have quite a wide variety of column vectors as I thought I did. In a certain sense, if I'm just thinking about the span, then 1, 3, 2 is redundant. I could delete it from my list, or I could keep it and delete the middle one, or I could keep both of these and delete that one. But as it stands, it is untrue that this set of vectors is linearly independent. I also want to make another comment about the kind of vectors that you can get by taking linear combinations like this. I could think of these columns with 3 numbers in them as being x, y, and z coordinates. I would be thinking of these columns as representing points in 3-dimensional space. Is every point in 3-dimensional space attainable by taking something out of the span here? We'll have to calculate and see. Let's look into this issue. Yes or no? Can I write the column 2, 3, 4 as some member of the span of these 2 things? Can I write it as a linear combination of them? The answer will be yes if there are numbers C1 and C2 that make this equation true. If there is no pair of numbers C1 and C2 so that happens, though, the answer will be no. So if you do the arithmetic, you find out for this to work, in order to make a linear combination to give me 2, 3, 4, 3 equations have to be true at the same time. That, and that. This one isn't going to be particularly difficult because if C1 is going to be anything, that first equation says C1 has to be 2. If I take that fact and put it into these other 2 equations, ideally that will tell me what the C2 is, and that's where the problem lies. This may say one thing, and that may say another. If that happens to us, there's no way to make this happen. On the other hand, maybe we'll get lucky. Let's see. So let's look at this second equation. 2 times C1 plus C2 must be 3. The first equation tells us C1 is 2, so this term is 2 times 2. 4 plus C2 must be 3. C2 must be -1. If we were naive, we would declare victory and say, you bet, you can do this. But the third equation hasn't had its say yet. The second equation demands that C2 equal -1. The last equation demands that C2 equal to 2. -1 and 2 are not the same number. There is no way to make all 3 of these equations true at the same time, no matter how you pick the C1 and the C2. In technical language, we would say that these 2 vectors do not span R3. There are vectors in R3, column vectors, where no linear combination of these 2 things will give you that column vector. So now I can make the definition that I've really been interested in here. A basis for Rn is a set of vectors that do 2 things. Number 1, they're linearly independent. There are no unneeded vectors. Secondly, they span Rn. If I have a basis, it's possible to prove, although I'm not going to here, that any basis has the same number of vectors in it. That number is called the dimension of the span, or as we'll be saying, the dimension of the space that we're working in. You already know one basis if you took third semester calculus. In third semester calculus, we wrote things as rows with brackets to indicate that they were vectors. This would be our column version of what we called I. There's J. If you're in 3 dimensions, I, J, and K. To further illustrate what I've been talking about, I want to show at least one of these 2 things actually is a basis for either R2 or R3. This kind of setup is called the standard basis. So let's show that the alleged standard basis actually is a basis. I have to do 2 things. Number 1, I have to show that this set of vectors is linearly independent, and then, number 2, I have to show that this set of vectors spans the space, spans R3. Suppose I take a linear combination of these 3 vectors, and I get the column of all zeros, the 0 vector. Obviously, you could do that by making C1, C2, and C3 all equal to 0, but the question is there any other way of doing it? It's a straightforward calculation to show that if C1 times the first vector plus C2 times the second plus C3 times the third comes up 0, 0, 0, then do the multiplications, add the vectors together. It has to be true that C1 is 0, C2 is 0, C3 is 0, and there is no other way to make a linear combination that gives you the column of all zeros. This set of vectors is linearly independent. Now I have to show the span of the space business, but that'll be easy. Pick some column in R3. These numbers, A, B, and C, could be anything. They're arbitrary. True or false, having selected one of those, can I always find coefficients C1, C2, and C3 so that the linear combination here comes up equal to whatever column I selected? Writing out the linear combination, I see that the answer that I'm going to get back is a column with 3 numbers in it. C1, C2, and C3 appear in the first, second, and third positions. This is because my basis vectors have so many zeros in them. Is there or isn't there a way to make that come up equal to that? To make that happen, C1 should be A, C2 should be B, and C3 should be C. So the answer to this question is yes. This set of 3 vectors in R3 are linearly independent, and they certainly span the space. Those 3 vectors form a basis. I want to look at one other example of this before I quit this video. I want to show that the set of vectors, the first one 1, 5, and the second one 5, 1, is a basis for R2. If I draw the straight lines that these 2 vectors will point along, it's kind of reminiscent of a space-time diagram. We'll talk more about that later. Right now, I want to show linear independence and the span R2 business. So we'll form one of these linear combinations and ask the question, to make this linear combination come up to be 0, 0, does that demand that both C1 and C2 be 0, in which case I'll have linear independence, or are there other ways of getting that result, in which case linear dependence? This is an easy enough system of equations to solve. If the linear combination comes up 0, 0, you have no choice. C1 must be 0 and C2 must be 0. The pair of vectors forms a linearly independent set. In terms of linear combinations, there are no unnecessary extra vectors. I'm going to select some column in R2, AB, where the A and the B are arbitrary. And I want to think about this. No matter how I pick the A and the B, is there going to be a C1 and a C2 so that I can make this happen? Or are there ABs so that I can't make this happen? In the first case, we'll say that the pair of vectors spans the space, and in the other one, it doesn't span the space being R2 here. This boils down to answering the question, does this system of equations have solutions, C1 and C2 values, regardless of what the A and the B are? If I look at this first equation, it tells me that C1 must be A minus 5 times C2. I'll take that and put it into the second equation, and after simplifying, I find out that C2 equaling B minus 5A over negative 24 will work. Notice that in the arithmetic I've done, there's nothing that can go wrong on me. I never get division by 0 or anything like that, regardless of what the A and the B are. Once I know that I can find a C2 number that will work, I could conceptually put it back in the first equation, and that would tell me there'll be a C1 number to go with it for the same reason. If you know more linear algebra type stuff, you could also comment that the determinant of the coefficient matrix is not zero, so that Kramer's method guarantees there's a solution. Any way you want to look at it, though, this pair of vectors forms a linearly independent set and spans R2. This pair of vectors forms a basis for R2. Coming up next, we're going to talk about dot products, eigenvalues, eigenvectors, and the spectral decomposition. I think that'll be enough linear algebra to hold us for a while. In the meantime, I hope everybody's having a good day. I'll talk to you again soon.